He's an expert in reionization and machine learning, probably other things as well. He got his start at University of Khartoum, Sudan, and then from there he did his PhD work in South Africa. And then after this, he's visited many places, MPA, and did a postdoc in New Mexico State University as a fellow there, and then has currently been a Flatiron Institute CCA fellow. So actually, next he'll move to Princeton, and he's very eager to keep in touch with people at Harvard here as well. So thank you.
Yeah, thank you very much for the invite and for the introduction. Yes, so I'm currently in the Flatiron. I'm going to Princeton in January, but I will look forward to spend significant amount of time visiting the CFA. So as Aaron mentioned, by training, I'm reionization person, cross machine learning. But I can tell you reionization is great because you basically interested in large scale and small scales, and everything that happens in the ISM and in the interstellar medium that really affects the generation of photons and everything. So that's why I became very interested in star formation models. Basically, we're trying to compare two models in cosmological simulation. So I can just tell you another motivation why. I'm interested in this, and I tell you much of the other motivations. So besides reionization thing, one of my first attempts to dive into small scales astrophysics is to look at DLAs. So I worked on a project for DLAs, and DLAs are profile in the liminal forest, and they usually sit around center of galaxies. So it's very dense regions. But then one of the simulations that I was working on is SIMPA simulation, which basically implements the Cromb-Hall's star formation model. And in that model, the star formation is related to the density of the molecular gas. So you need to form molecular gas in order to form stars. And to trigger the formation of stars in the early universe, you have to assume a metallicity floor. And that metallicity floor, it's just like a free parameter. You can assume it's like 0.1, 0.2, like 10 to the minus 3, whatever. It's a metallicity floor you have to assume in the beginning. Otherwise, you wouldn't form molecular hydrogen, and then you wouldn't trigger star formation in the early universe. So what I realized is that if you change that threshold or that free parameter, which is the metallicity floor, the DLA metallicity changes. So which means that the assumptions and the parameters that you include in your subgrid model for star formation, it really affects anything, and the DLA metallicity should not really be affected by how the recipe for star formation. So this is one of the motivations that I was really became interested in looking into star formation. So one of the models that we will talk about a lot today is the Sprengel and Henquist model. So it's a very successful model. It's basically a multi-phase model that you have a cold cloud embedded within a warm or hot medium. And then basically the star formation is related to the total density of gas. And you can apply a threshold for density to form stars and other things. But the main idea is that the star formation is related to the total gas, differently from the Cromb-Hall's model where it's really to the molecular gas. So in that paper, this is the earliest attempts where here they did run isolated disk galaxy like Milky Way type. And then they show that they can, by tuning the model, the subgrid model, to the Kanneke-Schmidt relation, the Schmidt relation between the relation between surface density of star formation and surface density of gas. They realized that they have this, the time scale for star formation, and if you tune that to 1 gig a year, you are basically your simulation, which is these dots, they can reproduce the Kanneke relation very well. So it's basically most of the models that we have in the market, they basically tune, you have some parameters to tune to reproduce some kind of observations. Other motivations, also most of the models that they do not really capture the varying ISM conditions that we know from the ISM simulations. they mainly largely also dependent on the resolution, the mass resolution and the mesh. And then all the, like most of the progress in the ISM simulations and how the equilibrium and other things controlled is not really implemented in these simulations. So this is basically most of the motivations that we want to develop something, we want to implement a model that is not really tuned to observation. It's mainly tuned to ISM simulations, and we want to see whether we can really do that. So one of the interesting simulations in the market is the Tigris simulation. It's the three-phase simulation. These are different Tigris runs. So in these simulations, what they do is that they simulate a slab, which you can represent as like a slab from a galaxy, disk of a galaxy or something. And it has one KPC on the horizontal side, and then on the vertical side, it's basically like you go up to 4 KPC in each direction. So this simulation is very sophisticated. It has much of the feedback and all these physics, and you see you have the resolution to resolve the actual clouds, and these are coming from different runs of Tigris. So the question is that can we really use this simulation to inform the formation of stars on large cosmological simulation? That's basically the main motivation here. So this led to the development of the PRFM model, which is the pressure regulated feedback modulated model, which basically based on an idea. I don't think it's a very new idea, but the idea is that the ISM conditions and the star formation, they co-regulate each other. So in order to, like, the amount of star formation happens, that depends on much of the ISM properties that you have, of course. And the ISM property is affected by the star formation. If you have recently supernova explosion, then you might affect all the ISM properties. So they regulate each other to arrive to equilibrium. So then in equilibrium, as you see here, the pressure, the vertical pressure on the disk in a galaxy should be equal to the weight. And then the pressure, of course, it's related here. And of course, the pressure here is you can calculate the pressure as the density of gas multiplied by the effective velocity of gas. This is one of the parameters that it's very hard to resolve in these cosmological simulations, which we can get from ISM simulation. So to the effective gas, and then of course the volume of the volumetric density of gas is basically the surface density divided by twice of the scale height. Right? Then you have the weight, which basically it has different contribution from different gravity, depending on which gravity you assume in the vertical side. So you could have a contribution from gas, from stars and dark matter. Most of the simulations and the models in the ISM, they do not really account for dark matter contribution. I think this is one of the interesting addition with this model, that you can account for something from dark matter contribution. And then if you solve that integral, you can get different solutions for what is the weight from the gravity from gas gravity or stellar gravity or dark matter gravity. If you combine this equilibrium equation together, right, you can basically, depending on how many weights you get. So if you ignore stellar and the dark matter contribution and you look only at gas, you can solve this equation and you can get maybe a linear equation on relation for the gas height in the disk. If you include the stellar contribution, you can get like quadratic solution. If you include the three contributions for each gas, you will get kind of cubic solution. So then this can give you some estimation about what is the gas height in the simulation, because it's one of the debate in the field, right? Is it resolved? Is it not resolved? So there are different opinions here, and I can give you my takeaway on this for.
A factor of 3, because we know that the cosmic rays and magnetic fields have equal contributions to the turbulence in the interstellar medium, so there should be a factor of 3 in the pressure. So I assume that sigma squared is the velocity dispersion of the turbulence.
Yes, yes.
But if you have also cosmic rays and magnetic fields with equal contributions,
yes,
you get a factor of 3.
That's right, but I don't think the simulation now they account for.
No, they do not, but the real world accounts for that.
Yes, yes, that's true. Yeah, that's right. I think they are running now simulations to account for all these, like the
Cosmic
rays.
rays.
Yeah. Then the measured, also the measured gas height in the simulation is also a tricky quantity to measure because you need to define what is the mid plane and you need to rotate the galaxy and all that. And then the definition that we adopt, it's basically if you have a column of gas, it's probably the height that corresponding to the half of the mass in the column. So this is the, so you get this estimation for the gas height, right? Now, before I go to so far I discussed only the pressure and the equilibrium, the pressure regulated. I will come back to talk about the feedback modulation. But then what do we need to implement this model, right? So we have this model now, we want to assume equilibrium. Also, they are, right, I mean, some people can say maybe galaxies at high redshift, they are not really in equilibrium. That's another issue with the model, but let's assume that we want to implement this model. Then you have, as you have seen from the equations here, from these different terms, this is probably what you need. You need from gas, you need to be able to calculate what is the surface density of gas around gas particles in the simulation. And you need either a way, if the gas height is resolved, then maybe that's enough for you, or other way you need to calculate the volumetric density of gas, and then because all these three are related. The same goes for stars. You need to know what is if you want to account for stellar contribution, of course. And for dark matter, you need only the volumetric density of dark matter. And then we need the gas velocity. I think these are most so if you are able to calculate these quantities on the fly, then you might be able to implement this model. And they are a bit tricky to compute. So let's talk about this because I think these are the easy one. So what we do now is we go to TNG50 where we have an output from the Springle and Henquist model, and we want to implement this model. So before you dive in on the fly, let's do this in post-processing. So you go to all galaxies in TNG50 at different redshifts. This is just a random galaxy. And then you compute all these quantities, right? You can compute as you see here, the first one is the surface density of gas. You have the surface density of stars. This is the star formation that you get from the Springle and Henquist model. And one of the things is that you see here, these regions do not really form stars because they do not really exceed the threshold for forming stars. That's why you see these disconnected regions in the model prediction. And then you have also the stellar height. You have the volumetric density of stars and dark matter here. So you can go and because we know that we want to tune everything to the ISM simulation, and the ISM simulation is coming from 1 kpc scale length, we try to generate all the maps from the simulation by assuming this 1 kpc resolution. So we have that, and that's really easy to do, right? Now we need to talk about the gas velocity. How do we do that, right? So we don't have the resolution to do this in the cosmological simulations. So this is where the ISM simulation really become very useful. So this is the relation between so basically when you don't have the resolution, you have to assume an effective equation of state, which is basically a relation between gas pressure and density. And this is, the ISM simulation here is the pressure as a function of density. And all these points is coming from different ISM simulations. As you see, this is the sigma gas here for the initial conditions for different of these the ISM runs. And you kind of, you are able to look at this, and there is a nice correlation between, because in these simulations they implement this equilibrium, and you see that, so there is a nice correlation between the total pressure and the density, which you can make a and then you get that fitting function, right? And then we know from the definition we have is the pressure is equal to the sigma squared density. You can solve these equations together to get some kind of dependence that the sigma gas or like the velocity of the gas is related to the pressure to the power 0.22. This is mainly just coming from ISM simulation. So now we have a prescription for how the gas velocity evolves. Then you can take that and you can predict what is the gas velocity for galaxies in TNG, which this model is not really existing in TNG, right? So you can go and calculate all the pressure profiles, and this is how the pressure changes from the evolution of the pressure profiles at different redshift. So all these profiles, it's not a single galaxy. I have to stress that. This is not a single galaxy. All these are a combination of 1 kpc patches in the ISM from all galaxies in the simulation. So this plot does not really discriminate between different masses and different, it's just like if you are within the ISM, 1 kpc resolution, you can compute these combined together. So then for the effective velocity, because it's related to that, you see now you have some kind of distributions, right? So at redshift of 0, the peak is around 10 kilometer per second, which is somehow like the value that, the nominal value that you find from observation, many simulation that I adopt. It's like around 10 kilometer per second. And then it goes up to 50 kilometer per second, depending on the environment, or depending on the pressure, of course. And you see that as you go to higher redshift, the pressure is higher, and then you can get velocities up to 150. But still, most of the distribution is here, right? So the peak of the distribution is here. So it's still around 50, but you can get some batches where they have some high velocity you can get. So now we have the velocity, we have everything. We can now go and make our comparison, right? So the first comparison, although I convinced you that we have this, we have a relation for the sigma effective. I want to use two things, right? So I want to assume, let's assume it's constant. The velocity does not change at all as a function of redshift or as a function of pressure or whatever. It's the same valid everywhere, which is 10 kilometer per second. It's like the commonly adopted values. And let's assume this and let's see, right? So then you go to your simulation. You can estimate what is the gas height from the simulation and with the predicted, the one that we predict if we assume equilibrium. So the top panel on the left is redshift of 0 and 3. This is all combined, the 1 kpc batches from the whole ISM. So the red is the measured one, the blue is the estimated. So if you assume 10 kpc, and it's very important to remember this is coming here, right? So the gas height, when you solve this equation, you have a strong dependence on the sigma effective. That's why the sigma effective changes things dramatically here. So, and then here it's, in this panel, this is the ratio between the measured and the estimated, and the dashed line is basically where you expect things to be very identical. It's like the identity line. So looking at this, right, you realize that if you assume equilibrium, you get much smaller height distribution than what you measure from the simulation, right? That leads to maybe a difference of 1 order of magnitude higher measured gas height than the estimated from the equilibrium, right? Which means that you can conclude the gas height is not resolved in this simulation. And most of people would be happy about that because most of the simulator believes that the gas height is not really resolved, right? So this is one of the, if you assume constant velocity. If you assume this relation, that the velocity changes with pressure, you arrive to a completely different answer. That the gas height, the comparison between the gas height and the estimated and the measured, they look really marginally together, right? So the peak within the same, I mean, there are still differences. If you look at the ratio between them, you kind of exceed the identity line slightly, but you can assume that it's marginally resolved. So it's basically the gas height in this simulation, it really depends on what recipe for the sigma gas you use. If you assume a constant gas velocity, then you can say, well, the gas height in this cosmological simulation is not resolved. If you assume a relation, whatever the recipe is, this recipe is coming from the ISM simulations. But if you assume that it's really related to the pressure, then you can conclude that it's probably marginally resolved. So the gas velocity is a really key parameter to this model. So now we can talk about the feedback, right, from the ISM properties. And then yes, so you can quantify the star formation either by the surface density of a star formation, or by the depletion time, which is basically the ratio between the sigma gas and the sigma star formation. Then the dynamical time could be defined by that. Any dynamical time should be like a velocity, like a length divided by velocity. So in this case, it could be the gas scale height divided by the velocity of gas. And then from this theory, what they realized is still similarly to the velocity that is related to the pressure. They derive that the star formation surface density is related to the pressure by this factor epsilon, and this epsilon factor is just like a feed yield back parameter that has a dimension of velocity. And then from this model, you can compute also the depletion time following this way, which is basically the relation between the depletion time and dynamical time. So now we have this free parameter, right? The epsilon, which we need to find out how to get that. And the idea is to go to the ISM simulation again. So in the ISM simulation, this is the same runs that you have seen before. This is a relation between this epsilon parameter and the pressure in different ISM models. And then basically you look at this, you can see, well, there is some kind of correlation that the feedback decreases as you go to higher pressure. Then you can make a fit. The scatter is very high here, of course, because this is a yield parameter which depends mainly on the feedback and the response of the supernovae and whatever. So there is a high fluctuations. That's why the scatter is much higher than what you have seen between the pressure and the density. So then you fit that and you can use this. So we have this now. You can apply this model. So if you are able to compute the pressure from the simulation, you should be able to get your feedback. And then once you get the epsilon, then you can calculate with the star formation, right? Now let's talk about the comparison at the level of the depletion time and the dynamical time. So what you see here is that this is on the left side, this is the PRFM model when you compute what is the depletion time for all these 1 kpc patches in post-processing from TNG 50, all galaxies at redshift of 0 and 3. And then here is what you get out from the simulation when you use the Springer and Hepworth, which is basically just dividing the density of gas by the density of the star formation. All these plots is color coded by the fraction of star formation. What is probably like this, the lighter the color, it means that these are the outskirts of galaxies and they don't have really much more star formation happening. The darker regions here, this corresponds to the center of galaxies. These dashed lines basically correspond to different ratio between the dynamical time and depletion time, and we kind of know, or maybe from local universe, that the ratio between these is like the depletion time is maybe 1% of the dynamical time, and that's why, and this is represented by this dashed red line. So the output of TNG, because TNG is basically the model has been tuned to produce this, you see that you're getting the same slope nicely in all redshifts. The prediction of the model, when we implement this, we realize that the slope is not the same. We don't have the same slope. And we have the tendency to go to a much shorter depletion time, which tells you that you have much more efficient star formation than TNG. So the model as it is now, if you use everything from the ISM simulation, you realize that you really efficiently form you efficiently form much more stars than TNG, right? This is if I assume 10 kilometers per second, right? If I assume the relation that you get from the ISM simulation, which is the sigma to the pressure, then you see if I go back and forth, you see that you go even to much higher, much shorter depletion time, which tells you that you can form efficiently much more stars than the TNG. So this is a big difference between the two. That the slope is different, and you tend to form stars much more efficiently. You can look into other one of the other, one of the Kennecott-Schmidt relation, I actually had a chat with Rob Kennecott, and he told me I don't really like people to say Kennecott-Schmidt relation. I think it's the Schmidt law, and it should be like that. I told him, no, I will still use, I will still use Kennecott-Schmidt relation. So this is the Kennecott-Schmidt relation, right? So this is the surface density of a star with the surface density of gas. Again, here is the Sprengel and Henquist, right? This is here the prediction that we have. This is the solid line. This is where you the Kennecott relation. These dashed vertical lines just like limits from 1 to 100 solar masses per parsec squared, just to show this is where we have data from ISM simulation. So these are these stars. These are the different ISM simulations that we took all the relations from. And you see here, and you see, right, so for the Sprengel and Henquist, because it's tuned to reproduce actually this relation by assuming 1 gig a year time scale for star formation, you see that it fits this relation quite well, right? So, and then if you go to, it fits that at high densities, and if you go to low densities, you see that you don't really form stars here, because they apply a density threshold to form stars. In our case now, we realize the first thing is that what is exciting here is that where we have data from Tigris, it seems to me the model really reproduced the Kennecott relation quite well. Without tuning to observations, you are able to, by just taking the ISM insights, you are able to reproduce this relation where we have data from Tigris, right? So anything beyond this region and that region, this is just extrapolation of the model. And if we go and extrapolate the model to lower densities, we realize that we continue to follow the Kennecott-Schmidt relation. And this is probably wrong at low redshift, because we know in low redshift, the relation you shouldn't be able to form really stars after that. We don't know whether this is true in high redshift or not, but for low redshift, we know that. So we probably might need to apply this. But anyway, if you look at this, the fraction of star formation here is really small, right? So it's really going to be very, very small. So it shouldn't really affect things much, very much. If you look at higher densities here, you realize that we exceed, we predict much more steeper relation, right? So it's much more steeper than the Kennecott relation. And this could be for many reasons, but I think it has been shown in many works that everything in this region, when you have this high densities, is a molecular gas. And if you make this CO correction for the relation, and wherever you kind of tend to have much more steeper relation between the gas surface density and the star formation surface density at high densities. But yeah, so what is exciting is that between these two limits, we really recover the same relation quite well. And I think with that, this will conclude my my presentation. Is that what I wanted to? Yeah. So let me before concluding that this is only for 10 kilometer per second, right? If you do the same you use the velocity relation to pressure, right? You realize that it doesn't really change much. It only affects, of course, it affects only the high density regions, because the relation is rather really steep, right? So in the beginning of when you have a low pressure, it's kind of almost flat, and then because of this 0.22, then you really peak at high densities. That's why you only, as you see here, you only affect the large density, but that it doesn't really change much the relation. So in conclusion, what my takeaway here is that the gas height in this cosmological simulation, it could be resolved, or could be not, depending basically on how you treat the gas velocity. What is your recipe for that? What we find is that we are really we are really consistent with the Kennecott relation, where we have data from ISM simulation without the need to tune to the observation. So that's really really exciting about this model, and yeah, what we have seen is that we really tend to produce shorter depletion times that leads to much more efficient formation of stars than TNG, which is, I mean, this is also we need when we implement this in the fly. things might change, and we want to see that. So it's a very challenging model, of course, because it depends. One of the problems we have with this model, how to implement in the fly. These are the quantities you want, and this is very challenging, right? So depending on this, what is the recipe? If you assume that it's really marginally resolved, then you don't need, like, you can really, like, for the gas height, then you can go and measure that from the gas height, right? But that also depends on what is the recipe you use for the velocity. So depending on your velocity, you can assume whether this is correct or not. This is one of the issues. Computing these volumetric quantities is quite easy because you can just grab a kernel and around particles and get that. The challenge is the surface density. How do you do that? There are many ideas to do this, but it's a very challenging quantity to compute around particles because you need to assume some geometry to calculate that. And now, depending what kind of geometry you assume, how big that geometry is, that's really one of the challenges we have with that. So yeah, so if you have ideas, I would welcome that, and I will stop here. Thank you very much. Maybe I should leave you in my...
I guess we can move first.
So the underlying assumption here is that there is some equilibrium between the energy or momentum input to the gas and the state of the gas. But we know that there are phases of starburst and AGN feedback that violate that, and then you get something quite deviant. And the question is how significant, in terms of the global star formation history, which fraction of the stars form under the other circumstances? And do you have sort of a sense, is it?
No, I think that since if we implement this on the fly, we would assume that in each global step in the simulation, that everything should arrive to equilibrium. So like
Starburst galaxies or AGN?
That should be automatically accounted for through the sigma and epsilon feedback.
Well, but we know there are outflows, so
That's
clearly
right.
it's not in equilibrium.
That's right. That's what I'm saying is that, like, at high redshift, it's probably dangerous to assume that, but at low redshifts, maybe it's okay.
Okay, but so most of the stars formed at this phase, you're saying? Most of the stars?
Yeah, if you follow this model, it's like that.
Most of the stars?
Yeah.
Okay.
So this relation between the gas velocity and the pressure, so you derive the exponent by fitting this relationship to simulation data. So it seems to me that after 3 or 4 view graphs in 5 minutes, this is essentially the assumption of the virial theorem. Right? And then in that case, that's not a unique solution. That's a family of solutions because there's another parameter in there which is the size scale. Right? And so then it doesn't necessarily give you the wrong answer because you're just using the simulation data to fit this. But it's not a solution. It's not a unique solution. So that's not a unique relationship.
Yes. That's
Okay.
why, yeah, that's why I mentioned that it's depending on what recipe, your favorite recipe, things will be completely different.
Well, if you were to derive that relationship from observations, then you would have, well, then that would at least fix that relationship based on that assumption.
Yeah, but I think the motivation here is to avoid, like, we want to do things from the ISM theory and then see whether we can really.
That's why this Koenig-Schmidt relationship works pretty well, because that is derived from the observations.
I wondered if you could talk a little bit about, and because you probably have insight into this, something that was striking to me is that when you start with these ISM simulations, it's this big turbulent mess, and as a result, there's variance that's kind of intrinsic there. And then when you're replacing that with this kind of deterministic relationship, I wondered how that propagates into something like a cosmological simulation. Like, is that variance an intrinsic important property of these sorts of things?
Yeah, so I think also one of the things we don't have, like, still the resolution is the issue, so we don't have the same 1 parsec resolution in cosmological simulation.
Right.
So that's why we apply everything in one kpc. Yeah, so the idea is that in these larger scales, in 1 kpc, you should arrive to equilibrium and you regulate everything, and that scatter shouldn't really affect much. However,
so it's like you're averaging over.
yeah, you're
a big
averaging
enough
over 1
volume.
kpc.
Okay. Okay.
That's
That is
basically,
kind of okay.
that's why you see here, like, each dot here is coming from ISM simulation, right? So this is
Okay.
basically a global quantity for that
Yes.
simulation. And each simulation is 1 kbc scale. So
I
basically
see.
kind of, as you said, it's averaging over.
Okay, and so basically on the scale then that you're resolving in the galaxy, in the cosmological model, the sort of like, almost like pixel to pixel variation in your prescription doesn't really matter. So,
Yeah, that's
okay,
the
interesting.
assumption.
Interesting.
Yeah. I mean, one of the things I made some comparison about, like, this relay, like the stellar mass star formation relation or whatever.
Yeah.
But I realize it's very dangerous to show because if you implement this on the fly, the masses will change, right? So
Yeah.
so it's not really a consistent comparison to do. But I could have shown other things if we have it on the fly, but it's still really,
Super interesting.
yeah.
Yeah, so I was wondering also about this discrepancy in scale heights. Can be interpreted as not as the scale height being not resolved, but disks being in non-equilibrium. So essentially, if you apply the model based on equilibrium and get different scale heights, then can you interpret it as a disk?
I think
being
that's
out-
that's another angle you can spin it this way. But mathematically, what you find is that this is really mainly just depends on what you have in the velocity. So whatever your assumption about the velocity, that really affects everything. Which was very, because like I talked to any simulator in galaxy formation probably, and most of them they tell me it's not really resolved. And when I find this, it was very surprising to me, like, okay, so now depending on this velocity, right, how we do that. And this is also one of the things is that most of these models, still they don't really account for really, most of the ISM simulations that it's there, it doesn't have really much lower metallicities, it's much more higher metallicity. So I think with more runs of these ISM simulations at different metallicities and different things, we can probe different parts, and especially these high densities and whatever. But I agree. I mean, I'm myself, I'm not convinced that galaxies, as the one who's really interested in reionization, I'm really convinced that like at redshift of 6, probably it's very hard to find a disk galaxy. And maybe they are not really in equilibrium, right? Galaxies are small and they have really high pressure and high feedback and all that. But it's still exciting to see that if you implement this just on post-processing, you still kind of represent, like, you match the relation automatically without like tuning to it. We have this interesting differences at high redshift and low redshift, at high densities and low densities, yes. But as you say, I mean, it could be a sign of the equilibrium is not really achieved.
Okay, and vice versa, if you put this relation, which was calibrated on simulation, and get the scale heights back, isn't this argument sort of like circular?
Yeah. It is of course, because here, when you do this solution, if you want to find out what is the sigma gas, right? Because the sigma gas depends on pressure, and the pressure depends on the gas, so you have to solve this iteratively, right? So you guess one solution, you say, okay, maybe the gas velocity is 10 kilometers per second, and then you iteratively solve these together till you arrive to convergence, which you can get very quickly. Probably, like I realized, like maybe 20 steps or something, you can really arrive to and that's why you see these differences here. That's why you see as soon as you implement this, everything is really pushed to a very large values because of this iterative solution. Because the velocity depends on pressure, the pressure depends on gas, and you have to. Yeah.
So I missed something, I think, quite basic somewhere. So the Springer-Hörnquist had a depletion time of 1 gigayear. And it works. It produces, nice looking galaxies. Your ISM model with this p to the 0.22 scaling has got a completely, look at these guys, especially show the 0.22 scaling slide. your depletion time is something completely different. Doesn't that mean that, if you went and did the on-the-fly calculation, it cannot reproduce the universe? Or am I missing something?
I think first of all, like if we look at the level of the Kenneckett relation, we show now it matches that where we have ISM simulation, right?
When this guy looks so different.
Yeah. So when you have that, what we expect is that we might have much more star formation happening, especially from high redshift. But most of these global quantities, they have a large scatter as well, right? So if you look at how the cosmic density of star formation relation, like the Maddow famous plot, or if you look at other the stellar mass and whatever, there is a scatter there. But I can't really comment on that yet because we don't have that. But I think what you can see here is that you efficiently forming much more stars. Now we are relying whether the scatter in the observation is large enough that we still fall within the same.
Go to the next slide. Go to the next slide.
Okay.
Look at that.
Yeah.
There's no relation at all between the two sides. How can
The slope is different. Still, there is still the scatter is not really high here, right? So still there is, but the slope is different.
Yeah.
From it's not. It's basically probably dependent on the dynamical time rather than a constant between the depletion time and the dynamical time.
Is there just a difference at the highest surface densities in the Schmidt relation? So if you flip back and forth at the
That's right.
relation there.
Yeah, that's
Say
right.
that again?
This is basically this
Here,
difference.
if you
that-
flip back and forth, there's like a change by a factor, by an order of magnitude at high
Yeah.
surface densities.
But at high redshifts, you're mainly forming stars.
You're going to be there,
Very
right?
high dynamic.
Yeah.
Yeah, so all the high redshift will have very high efficiency, which means all your galaxies will be bulged out in it. There will be no disks by the time you get to redshift 2 or 3.
So Tigris should be pushed to that regime. Are they doing it?
To reproduce the Kenneckett relation?
No. To the high sigma regime. Because your blue stars are limited to sigma less than 10.
Yeah. Limited to this.
Yeah, but is Ostriker and Kim doing ISM simulations at higher sigma?
Now we are running more of the simulation at lower metallicities, higher sigma and whatever. But as I said, still there are some works shows that this relation steepens if you account for depending on the conversion factor of CO for the molecular gas, because everything here is molecular. You can see this steepening happens. And they are also like the semi-analytical models and whatever, they also implement these the same steepening from.
But the molecular Kenneckett-Schmidt relation also has very high depletion times. So you cannot have very low depletion times even in molecular gas, right?
Yeah, it doesn't steepen as much, but still there is some kind of steepening even in the molecular Kenneckett relation. You can see this steepening, but it's not as high as here. I agree.
By the way, a few hundred solar masses per square parsec is where the Thomson optical depth is 1. Something changes qualitatively in terms of opacity of the gas.
Yeah, I mean the assumption is that you can, on the scales of 1 kbc on large scale simulations, you can probably just assume that each one of these patches is one of these ISM simulations, and then you can average over. That's the assumption. That's why we are pinning everything in 1 kbc scales. But things, as you said, and if you go to the fly, things might completely change. And as a first test, like one of the tests I did is that like if you sum all the star formation you get from these different models, you get a factor of 1 to 2 order of magnitude difference in the total star formation as a function of redshift. You can see that. But that is also not, it's very, that might change if you do this on the fly, right? Because that recipe also depends on what is the feedback in the simulation, what is the galactic winds and other recipes, right? As a part of this collaboration, we're also trying to implement another model for galactic winds that is led by Drummond Fielding and Matt Smith, who used to be here. So the hope is that we can combine these two models together. Maybe they can really work well. But yeah, so I found that a difference. Another difference I found also is that if you look at the stellar mass and halo mass relation, like the stellar mass and the halo mass relation, you find also a big difference, maybe like up to 2 order of magnitude different. But that, like the stellar mass, will change if you do it on the fly. So it's also not really a consistent comparison, and you can't really draw. I mean, the only thing we can do is really just to go in the fly and
See what you get.
do, so you see what you get. But at the level of the global star formation, because the scatter is high of the observation, we still the same in the scatter. So if you plot if you plot, I don't know, there is no board here, but if you plot the like at redshift of 3, let's say, you could have the observation in the middle, and the output of the Springer and Rehnquist is down, and our model is up. But the distance between the two and the observation, between the fit in the observation, up and down is the same. So you can't really say this is, right? That's at the level of the global star formation. For the level of the stellar mass also will change, so we don't know. And there are other things, right? Like when you go to the cosmological simulation, you would have like AGN feedback, you would have other quantities that might maybe suppress the high densities things, so there are many other effects, it's not included. This is just only a test in the fly and on the post-processing, and it seems like within the range we have ISM simulation, it kind of works. Now, I think one of the nice thing here is that like you are able to disentangle, right, the equation of the equation of state from the actual ISM model. So you have control on that, right? So now depending on what equation you want to assume, right? This effective equation of state, then now we have a control on this, right? So now you can, depending on whether you have more ISM simulation or whatever, this you can vary, you can change. That's, I think, one of the nice things. So I think the things is that here, the effective equation of state that you get, and this relation, these are the two things that coming from ISM simulation, the feedback and the pressure. But yeah, once we implement in the fly then, but it's still very challenging to,
So to what extent, when you have the cosmological model, can you evaluate some of these like equilibrium assumptions? So if you think you're starting to resolve some of these features, or maybe especially in regions where the scale height is large, you might think that you are resolving it. So can you ever ask to what extent like the sort of pressure equilibrium of the scale height is realized? Can you ask like how far out of equilibrium is this gas?
One of the things I'm doing now, but it's is to look into, if we assume all these things, right? If we are in equilibrium, the pressure should be equal to the weight. Right? So one of the things that I'm trying to do now is to go to the actual TNG simulation and take,
ask whether that's
yes,
true. Yeah.
whether that's true or not, right?
Yeah.
Regardless of the ISM recipe,
Right.
So you go and calculate what is the weight in all the disks,
Fantastic.
and then what is the pressure
Amazing.
from there. And then if they are the same, that might say that this recipe is correct.
And it just strikes me
this
that
recipe is correct.
as you go to very short depletion times, or short dynamical times, where you are also getting short depletion times, it kind of makes you wonder whether those are specifically the conditions that are out of equilibrium, and then maybe that affects the efficiency of that slope. It'll be really interesting to see.
This is exactly what I'm doing now.
That's so great.
To see, because if they are the same, then yes, the gas height is resolved.
Right.
Then probably the relation that we're getting from Tigris that relates the sigma and the pressure is correct, maybe.
Amazing.
Maybe it's a good one to use.
Yeah.
If it's not the same, right? If we don't see similar correlation like this, then probably, I don't know, maybe I did something wrong.
There's always time to figure that out later.
Is that this case like pressure just is imposed by the effective equational state in the ISM? So it's not some, I mean, it doesn't relate to turbulence or like star formation happening in disk. It's just something that comes from the.
So this is the total pressure, but in their actual ISM simulation, they account for different, like the thermal.
Right. But I mean, if you go for this test in the simulation in the TNG, right? So their pressure is imposed by the equation state.
Yes.
So you essentially like learning something about this model, right? Not about like whether galaxies are in equilibrium or not, but whether the ISM model has sufficient equation of state to ensure equilibrium of disks or
Is that true though? Aren't you asking like whether the large scale flow in and out of the disk is in equilibrium with whatever pressure you prescribe? I don't know how it works.
Yeah, I mean, the pressure in the ISM is prescribed, right? So
Right.
there's like a model
Yeah.
for pressure, and then
Yeah.
you compare it with the dynamical weight of the disk.
Yes.
So then you're essentially like asking whether the model is such that it allows the pressure to adjust to like the weight of the disk.
Aren't you kind of asking how hydrostatic it is though? And
Right,
that
right,
in
but-
itself is a question, I guess.
Yeah.
Isn't it?
Yeah, but it's not like a question about like star formation and turbulence in galaxies, but it's a
Right.
question about like specific equation of state imposed by the model.
Okay. Okay.
Right,
Yeah.
that's my understanding, right?
In this case, it'd be better to, also look at other models as well.
Yeah.
I see. Interesting.
Yeah.
Are there any further questions? All right, let's adjourn.
That is completely circular, that figure.
It is a-
Circular reasoning.